a little bit later this week with the Calculus 6, but to make up for it, we've got 6 fantastic problems for you to sink your teeth into. So see if you can solve these. If you do want a little hint for question 5, feel free to kind of fast forward to there to get the hint, pause it and then have a go, because I do believe you would get some kind of nudge in the right direction for how to attempt a problem like that. But pause the video, have a go at the problems, and the solutions are going to follow shortly. So let's get started with question 1. So we've got here that y is sine to the power of 4x, and we need to differentiate this. So we're going to go and use the chain rule here. So I'm going to let u be sine x, and what I'm then going to do is find my dy by du, and then find du by dx. We differentiate sine, we get cos. Now, what I now need to do is do dy by du times du by dx. Which gives me the following, and then I just want to substitute back in u equals sine x. Okay, and that's my first problem. As I mentioned with these ones before, I'm showing you kind of the extra steps with the chain rule, but as you practice more and more, you probably will find quicker ways of doing this, but here's just kind of full process, and the chain rule is always good to fall back on if ever you're in doubt. So we're going to move on to question 2 now, where we have a function multiplied by another function. So when we have this situation, we want to use the product rule. So what I'm going to do is I'm going to let u be cos 7x plus 2, and I'm going to let v be natural log of 6x squared. So du by dx, as part of the product rule, I'm going to need to find the derivative of the first function. When I differentiate that, because there's a 7 in front of the x, the coefficient of x is 7, I'm going to need to multiply this by 7, and cos will go to minus sine. And you can check that with the chain rule if you're not sure. So now I need to find dv by dx. So what I'm just going to do to the side here is see how we can differentiate natural log of 6x squared. So there's a couple of ways you can do this. What I'm going to do is I'm going to use the chain rule to differentiate the natural log of 6x squared, but you can also use laws of logs if you prefer to sort this one out. So just because I've already used u, I'm just going to use a different letter here. So I'm just going to let the bit in the bracket be m. So m is going to be 6x squared. And then if I did dv by dm, that becomes 1 over m. And if I did dm by dx, when I differentiate the 6x squared, that becomes 12x. So my dv by dx would just be dv by dm times dm by dx. The dm's would cancel. So that's 12x over m, which becomes 12x over 6x squared, because I let the m be 6x squared. Just simplifying that, that just becomes 2 over x. Now, as I said, you can use laws of logs to sort this one out. You could also, as you get more practice with this, you will just notice that actually all you need to do when differentiating natural log of some function is you put what's in the bracket on the bottom of your fraction on your denominator, so the 6x squared in this case, and on top you put the derivative of that, so 12x. So, in time, you'll pick that up if you haven't already. So, my dv by dx is 2 over x. And now applying the product rule, what I need to do is my first function, which is cos 7x plus 2, and multiply it by the second function differentiated, okay, the derivative of the second function. So I'm going to do 2 over x times cos 7x plus 2. And then I do the derivative of the first function multiplied by the second function. Okay, and that's it for problem 2. As said, if you've got quicker ways of dealing with certain parts of it, that's absolutely fine. I'm just trying to show all the steps so you know what's going on, and then in time you'll probably kind of get quicker with this. So we've got a really nice problem now for question 3. Definitely looks like quite a funky problem, this one. We're doing e to the power of tan x. So let's see how we could deal with this. Now, this video has been very chain rule heavy, and this one's going to be no exception. So what we're doing here is, okay, we're thinking, well, I've got e to the power of something. I know how to differentiate e to the x, so I'm going to call that power u. So I'm going to let u be e to the power of tan x. So I try and find, so I've, dy by du, that's easy enough, e to the u. But then when I come to find du by dx, well, I need to think about, well, how would I go about doing that? So what I'm going to do, told you this was chain rule heavy, I'm going to use the chain rule within the chain rule. So over to the side here, I'm going to say u is e to the m, where m is tan x. Okay, because what I'm trying to do is I'm trying to differentiate e to the tan x, so that I can ultimately differentiate my e to the tan x. So I'm just going to call the power there m. So du by dm, so differentiate u with respect to m, that would just be e to the m. And then dm by dx, well, that means differentiate m with respect to x. So I'm going to have to differentiate tan x here, which is just sec squared. That's the result that you can find in your formula book. So what I was trying to ultimately find was du by dx. So if we times e to the m by sec squared, but remembering that m was tan x, I get this result here. So that's my du by dx. So we'll come back over to this left-hand side now. And now I have my du by dx. Now I can finally find dy by dx by just doing dy by du multiplied by du by dx. So just multiplying this all together, but knowing that my u is e to the tan x. Okay, so I'm doing e to the u times by sec squared times e to the tan x. So e to the u is e to the tan x. Okay, remember u is e to the power of tan x. So that's what that bit's going to be. And I'll multiply that by my du by dx. The bracket's not necessary here, but just to make it clear that I'm multiplying, I'm just going to put that in there. So a nice little problem. Well, at least I think it's nice. Just one that's really getting you thinking and really, getting you using the chain rule there. So we're going to move on to the integration problems now with problem 4. Last week we did a similar problem to this one, but differentiating it. So let's see how we could integrate something like this. So firstly, what I want to do with a problem like this is I want to rewrite it as 4 times 5 minus 3x to the power of negative 4. So I'll often want to rewrite a problem such as this one. So now what I'm going to do is I'm going to try and predict what the result would be. Because I reckon the result of this is going to be something that looks a little bit like what we have, but with a higher power of 5 minus 3x. So what I'm going to do is I'm going to try y equals 5 minus 3x to the power of negative 3. So basically just raising the power of the bracket by 1. And what I'm going to see is, if I differentiate this, do I get the result that I want? So we're going to differentiate this, and what do you know? We can use the chain rule to do that. It's still here. So we're going to do y equals u to the minus 3, where u is 5 minus 3x. And I find dy by du. So multiply by the power, take 1 off the power. And then find my du by dx, which is minus 3. So dy by dx is minus 3 u to the power of minus 4 times minus 3. So that's 9 u to the minus 4. But then I put my u back in. My u is 5 minus 3x. And I get that result. So I'm close. And what that's telling me is that if I integrated 9 times 5 minus 3x to the power of negative 4, that is what would give me 5 minus 3x to the minus 3. So that's almost what I wanted to happen, but not quite. I don't want to end up with a 9 there. Okay, I wanted to end up with a 4 there instead. So to adjust this, all I simply need to do is just multiply this thing that I'm trying here by 4 over 9 instead. Okay, so what I tried was almost right, except for when I differentiated that, I ended up with a 9 there. So to make sure I end up with a 4 there instead of a 9, I just multiply 9 by 4 over 9 to get the 4. So that's why I'm putting a 4 over 9 in front of the bracket rather than a 9. Rather than having nothing there. So if you're in doubt with that one, you could then go and differentiate that back to check it. Gives you a 4 in front of the bracket as required. But you can use this method to try these things. Yet again, you will probably pick up quicker methods of doing this as you practice. But do be careful with integration, that it is a lot trickier than differentiation, as you probably found out by now. In that, if this is 3x squared in the bracket, this suddenly becomes a lot more harder to solve as a result. So do take care with these. Right then, question 5. Now, question 5, I'm going to give you a hint on the next slide. If you want to have another go at this with this hint, then you can pause at this point. Okay, so the hint for question 5 is that we can use some trig identities to help us solve this. Okay, just integrating it as it is here is going to be very tricky to do. We can't just simply add 1 to the power and divide by the derivative of sine. That does not work. Okay, if you differentiate that back, you'd find that it doesn't work. We're going to need to use some trig identities here. Now, I think if this was a question in your exam, I imagine they would give you this hint, okay, or you'd have a show that this, or something very similar to it. So if you want to pause here to see if you can prove this trig identity, you can do. The result of this, I'm going to show as well how we actually can get this identity. So what we'd do is the sine 3x, I would rewrite as 2x plus x. Okay, that's just 3x is just the same as 2x plus x. And the reason why I want to do that is I can use my addition formulae that I get in the formula book to help me prove this. So I can rewrite sine 2x plus x using the result in the formula book that sine of a plus b is sine a cos b plus sine b cos a. Okay, that result is in the formula book. So this can get rewritten as sine 2x cos x plus sine x cos 2x. And then what I can do is sine 2x can get replaced with 2 sine x cos x. That just comes from using the double angle formulae. Times that by cos x. So remember, your double angle formulae, I really would recommend that you do learn it, but you can derive it from the addition formulae in the formula book. And cos 2x, I would replace that with 1 minus 2 sine squared x. And that's another use of double angle formulae. With cos 2x, you do have a choice as to which you use. I would recommend that we use the one that just has sine in, considering that my result is all in sine. And then we can start to simplify this. So 2 sine x cos x, well, that's 2 sine x cos squared. And now I'm just going to expand this bracket here out. Sine x times 1 sine x times minus 2 sine x minus 2 sine cubed x. And I've nearly got everything all in terms of sine here. What I could do next is change that cos squared to a 1 minus sine squared. Again, more trig identities. Trig and calculus just goes hand in hand, so it is so important that you're confident with your trig as well. So 2 sine x times 1 sine x, 2 sine x times minus sine squared minus 2 sine cubed. This is looking promising. We can then just collect together the sines and then collect together the sine cubes. Okay, and there we have it. We've shown that sine 3x is 3 sine x minus 4 sine cubed. So the question you might be asking is, well, why did I do this? Well, let's go back to the problem. We just showed that sine 3x is 3 sine x minus 4 sine cubed x. And what I could do with that is I could rearrange this to make sine cubed the subject here. 4 sine cubed there, and then I could just divide through by 4. And now what I have is two terms that are a lot easier to integrate. So rather than think of this as sine cubed, I'm going to think of it as 3 over 4 sine x minus 3 over 4 sine 3x. So I'm going to pull out that common factor of the 3 over 4, and I'm going to integrate sine x minus sine 3x. And the result of that would be, if I integrate sine, I get negative cos x. Just be really careful. Remember, when you integrate sine, you get a negative cos. If you integrate minus sine, you get a positive cos. But don't forget that we've got the coefficient from the x is a 3. So you need to divide by a 3, or multiply by a third. And don't forget r plus c. And then I'm just going to times out by that 3/4. You don't need to times the c by the 3/4 though, because it is just a constant. Okay, on to our last example. And you would think that integrating sine cubed would be easier than integrating cos x times sine cubed. Okay? But actually this is pretty straightforward. We can just do this pretty quickly. And if you want a little hint for this one, I might have already given a hint to this problem earlier in the video. Okay? If we go right back to the beginning, we showed that when we differentiate sine to the 4, we get 4 sine cubed cos x. That's a very similar result to what we're trying to integrate. So, earlier, we pretty much proved this result. Okay, we proved that if we differentiate sine to the power of 4, then we get 4 sine cubed cos x. So that means if we integrate 4 sine cubed cos x, we get sine to the 4 x plus c. So therefore, all I'm doing here is just integrating a quarter of that. So my result will just be a quarter sine to the power of 4. Okay, this is integration by recognition here, and just recognizing that the sine, if you differentiate sine, you're going to get cos. So it's, trying to spot these little patterns and these sort of how these are linked together to help you solve. But let me know how you got on with the 6 problems. Any particular problems you'd like to see more of, let me know. And just over a month to your A-level exams now, so keep practicing lots of calculus as well as the other topics as well. And yeah, all the best for the month, well, couple of months ahead.